everyone. So yesterday's lesson focused on ways that we use the first derivative to analyze functions. Today we're going to analyze functions using the second derivative. And so what the second derivative tells us about a function is something called concavity. And that has to do with which direction the graph is curving. Now you're already familiar with this concept, even if that word doesn't sound familiar. So for example, a graph that's concave up is opening upward like this. So this is concave up. We've talked about this with parabolas, but now we're going to talk about it with functions in general. And then, of course, your frowny face, that's concave down. I did not think out my spacing on this page here, but concave down would be curved this way. And then an inflection point is where we switch from one to the other. Okay, so an inflection point is where that concavity changes. So looking at this function that I've given you here, you can see that this left side of the graph has that downward curve, right? This is concave down, whereas this side of the graph is concave up. And then somewhere in between here, and you can't tell this visually, inflection points, you can't point to on a graph, you have to calculate them. But somewhere in here would be a spot where we would say, okay, that's no longer being concave down, now it's switching to be concave up. That's your inflection point. Okay, and so the thing that controls your concavity is your second derivative, and here's why. So my derivative here, down on this left side of the graph, right? My slope of my tangent line is going to be a really steep positive number, so a really large positive number. And then I want you to think about what's happening as I move forward, right? This is all decreasing, right? My slope is getting, more shallow and more shallow until it reaches this point here where it's exactly 0, okay? So this is all a decreasing derivative. Well, if the derivative is decreasing, then that means the second derivative, which tells us what's happening with the first derivative, right? My second derivative would be negative, right? Because the derivative of a function that is decreasing has to be negative, okay? So what that tells us is this portion of the graph that's concave down is going to have a negative second derivative, okay? And this would continue to be decreasing because it goes to 0 and then it turns negative. So as it turns negative, that's still decreasing. So we would still have a negative derivative of the derivative, a negative second derivative. But somewhere in here, we turn around and start turning back towards 0, right? And if we're turning back towards 0 from something that's negative, so this is a negative slope and we're approaching that 0, right? We must be increasing again. And so that place where our derivative turns around and starts heading back towards, or starts increasing again, starts heading back towards 0, that's where we suddenly have this concave up portion of our graph. So this would be where our second derivative is positive. And so then it should probably make sense to you that if what's controlling your concavity is that second derivative, that inflection point is where this is switching from negative to positive, meaning at the inflection point, our second derivative is exactly 0. So that inflection point is really going to behave a lot like a critical point did when we were working with the first derivative, okay? Except it controls where the concavity changes, not where the direction changes. Okay, so let's take a look at this example 1. And again, this should feel very similar to you from what we did yesterday with the first derivative. So if we're talking about concavity, we need to be looking at a second derivative. So as soon as you see concavity, you should be thinking, all right, I need a second derivative. So my first derivative would look something like, let's see, 6x squared minus 28x plus 22. And then my second derivative would be 12x minus 28. Okay, so that's just basic derivative rules, right? So before I can determine where I'm negative and where I'm positive on my second derivative, first I need to find that point where it changes, right? The inflection point. So I'm going to set my second derivative equal to 0 and solve this. Now this doesn't work out super nicely, but I'm going to add the 28 to the other side. and divide by 12, and I end up with x is 28 over 12. That is my inflection point. So that's where I know my concavity will change from one to the other. So we need to figure out, what is my second derivative doing on either side of that inflection point? So here's that inflection point. And just like we did before, I'm going to use test points. So I'm going to pick something smaller than 28 over 12. My favorite thing would be 0, right? Now, 28 over 12 is a little more than 2, right? So I just need to pick something bigger than that. So maybe let's pick, I don't know, 3. If you really wanted to go easy on the mental math, pick something like 10, right? And I am plugging these into the second derivative. So this is the second derivative that I'm testing. Okay, so here's my second derivative. If I put a 0 in there, I'm going to get a negative 28 out. So that means that this all has a negative second derivative. If I plug in something like 3, 36 minus 28, that's going to come out to be something positive. So to answer this question, because remember, this isn't enough to answer the question. To answer this question, I would say that I am concave down on the interval from negative infinity, because that's over here, up to 28 over 12. I might have cut myself a little short here in space. And I am concave up on the interval starting at 28 over 12 and heading out to positive infinity, because that's over here. So it works just like increasing, decreasing, except it's telling you something different about the graph, right? It's telling you the curvature of the graph, which tells you how quickly your derivative is changing. Okay, the second example is actually a really good one to kind of pull everything together. So I actually think I'm going to make a second video for that, just covering this example, because it's a good example of everything. But let's go ahead quick, and this is the same thing I did in class. Let's talk about examples 3 and 4 real quick, because these things are new, right? These are things that we haven't talked about before. Okay, so we're back to this idea of a tangent line, right? And I'm very confident that I could tell all of you, I could give you this equation and say, write me an equation for a tangent line. And you would know that I would need a derivative, right, to get your slope, plug your -1 into your derivative, plug -1 into the original function to get your point, write your equation, right? And the reason we write those tangent lines is so that we could make estimations about the original function. And now what we want to talk about is that estimation an under or over estimate? And what I want you to take away from this is that this question is really asking you about concavity. Oh, and I spelled concavity wrong. That's embarrassing. Here we go. Concavity. Okay. So as soon as you see that question, know that what I really want to know is, what direction is the concavity going? Here's why. Here's a graph that's concave down, and here's a graph that's concave up. If you think about where the tangent lines go, anywhere on this graph that's concave down, when I draw myself a tangent line, that line is sitting up above the graph, right? So if I were to use, let's say, this line right here to make an estimation about the function value, my estimate would be here and the actual function value would be here. My estimate is above the function because that's where the tangent line sits. So this is always going to give me an overestimate. If you're concave up, if you draw those tangent lines in, and I'm being kind of sloppy with these tangent lines here, but that line always sits below the function, right? And so if that line sits below the function, again, if I was to try to use, let's say, this line right here to make an estimate about this point value, my estimation from the line is always below the function itself. So this is an underestimate. I don't memorize that, by the way. I draw this picture, or at least think of it every time in my head. Okay? So what I need to know here is, which direction is my concavity at -1? So let's find a second derivative here, because that's what I need to talk about concavity. Negative 6x squared plus 3. My second derivative is negative 12x. And then remember, I want to know what is the concavity specifically at negative 1. So my second derivative at negative 1 would be negative 12 times negative 1, which is 12. Okay? That's positive. A positive second derivative means I'm concave up, and that means that my tangent line will always be an underestimate. Okay? So let's see, I wrote probably too big here, but maybe I'll write up here what my answer would look like as far as my justification goes. I would say that the tangent line is an underestimate because f double prime of negative 1 is positive. So f of x, whoops, not f prime, f of x is concave. Pretend that says concave up. That's my justification. I want to point something out here. Look at the way I wrote this specifically. That is a very concise, very condensed way to say what I just did here, right? That is the most efficient, most specific mathematical way to say this. Some of us are very wordy in our explanations. Some of us like to say, well, I calculated the second derivative and then I plugged in negative 1 and I got 12 and 12 is positive. And they say all of that in words. And this accomplishes all of that, right? You were saying, I calculated the second derivative at negative 1 and it's positive, okay? So try to start getting comfortable with that mathematical notation because it just cleans up your answers. It makes your answers so much less wordy. It makes it more clear what you're trying to say, okay? The second thing is, notice that I said f double prime specifically at negative 1. I didn't say f double prime of x, because f double prime of x could be negative or positive, depending on what x is, okay? I also did not say 12 here. I said that it's positive, because nobody cares that this is 12. What we care about is that it's positive, right? So that's what you want to make sure you have in your justification, okay? Okay, let's take a look at example 4. So example 4, this is kind of leading you into what we're going to do in the next lesson, where we talk about graphs of functions. And this is going to happen a lot, where the function that I give you to look at is actually f prime, okay? So if I am looking at f prime and I am asking you questions about f double prime, I'm really asking you about the derivative of this graph. So if I want to know where f double prime is positive, what I really want to know is if f prime is increasing or decreasing, okay? Because if f prime is increasing, like for example on this portion of the graph right here, if f prime is increasing, that's going to be a place that f double prime is positive, right? The derivative of this graph would have to be positive. And that's going to be true anywhere here that we're increasing. And I was probably a little dramatic with the number of bumps that I made this graph have. Like, we could have made our point with fewer hills, but so everywhere that my graph is increasing, I have a positive second derivative. And anywhere my graph is decreasing, I'm going to have a negative second derivative. So like this portion of my graph here, I'm going to have a negative second derivative. So the point I really want to make here, though, because most people are able to get that part. Most people are able to say, like, okay, where it's increasing, I have a positive second derivative. Where it's decreasing, I have a negative second derivative. Where does that mean the inflection points are, right? The inflection points are when we switch from one to the other. The inflection points are the place where we're exactly zero in between these two. So my inflection points, see, I need a color that's going to stand out here. Sorry, making a lot of color decisions back behind the scenes here. My inflection points are going to be these places here, my mins and my maximums, because that is where my direction is changing, okay? So to answer this question down here, the inflection points occur when there is a change from increasing to decreasing, or decreasing to increasing, right? Where that direction changes. In other words, it's where you have your relative extrema, maxes and mins. And that's going to be a really important thing leading into tomorrow's lesson. Okay, so I wanted to talk about it today while we're talking about all this vocabulary, that when you're looking at f prime, your inflection points are happening where this has a derivative of 0, right? Where you've got those horizontal tangent lines. Okay, that's probably it for today. Like I said, I would recommend coming back and looking at that example 2 video because it does a good job of pulling together all the first derivative and second derivative stuff. But otherwise, this should be enough to get you through for today.